All right, guys, so hopefully by now you've had a chance to work through that candy machine applet. And so we're going to start this section of the notes with sample proportions by kind of looking back at that project that you would have worked through and kind of looking at some of the differences between a few of these different distributions. The first is in the context of the candy machine applet. Let's talk about what the distribution of the population was. So the distribution for your population is essentially the expected values based on the claimed proportion. In other words, what would you actually expect if that claim was true? So if they told you that 20% were orange, 30% were yellow, and the rest were red, then what would be your expected number for each of those in a sample of size 10? That would be the distribution of your population. Next, let's talk about the distribution of your sample. So the distribution of your sample is slightly different in that this is the actual values which are obtained from your sample. So let's say for the population distribution, you expected to have 2 orange, 3 yellow, and 5 brown. But then in your actual sample, you had 1 orange, 3 yellow, and 7 brown. Then your sample distribution, or your distribution of the sample, would be that actual values that you obtained. Last but not least, let's talk about the sampling distribution of your sample proportion. So not just your single sample, but your sampling distribution. This would be the proportion, or represent the proportion of the orange candy, because again, remember we were interested in orange. So the proportion of the orange candy for all of the samples. So we're no longer looking at just a single sample and looking at the proportion of orange candies, but now we're looking at it for all of our samples. So our sampling distribution of that. So for the next question, based on that candy machine applet, describe what we know about the shape, center, and spread of the distribution of a sample proportion. Let's start with the shape. The shape, I'm hoping that what you found was eventually you got it to be approximately normal. And that's going to be the case for most sampling distributions. As long as you get to a large enough n value, you're going to have a shape which is approximately normal. Now, how big? We'll talk about that here in just a little bit. Next, let's talk about the center. The center of that distribution, hopefully you noticed, was pretty darn close to the claimed proportion P. And again, as you got to larger values, that got closer and closer and closer. Last but not least, let's talk about the spread. The spread really shouldn't have changed a whole lot. This was pretty much the same and did not change based on your sample size. So when is it okay to say that the distribution of your sampling distribution p hat is approximately normal? Well, that's when the sample size and your number of samples get to be large enough. So when the sample size and your number of samples were large. That's when it's okay to say that it's approximately normal. So let's talk a little bit more about each of those criteria, because we're going to be using those a lot when we talk about these sampling distributions. So first, let's talk about the mean for our sampling distribution for a sample proportion. So the mean of our sampling distribution, the mean of p hat, should be equal to p. The nice part is you don't have to worry about any conditions there. You can just go straight to that. Next, let's talk about standard deviation. So the standard deviation of our sampling distribution of a sample proportion is as follows. The standard deviation of p hat is equal to p multiplied by 1 minus p over n. It's also worth pointing out that both of these two are on the formula card. So these are things that you do not need to necessarily remember how to find for yourself. Now, here is one of the drawbacks to standard deviation is, once again, there's a condition that must be met for this. So if you remember, there was the condition of independence when we talked about how to combine random variables. Now that condition is what's called the 10% condition. So let's see what that says. It says that in order to calculate your standard deviation, you must sample no more than 10% of your population. So as an inequality, you could write that one of two ways. If you write it the exact way that we just said it, we would say that the n is less than or equal to 1/10 capital N. In other words, your sample size must be less than or equal to 1/10 the size of your population. Probably the easier way to think about it, though, is to multiply both sides of that inequality by 10, and you arrive at this, that 10 multiplied by n is less than or equal to capital N. In other words, 10 times your sample size must be reasonably less than your population size. Last but not least, we have our large counts condition. And by the way, large counts is what establishes whether or not we can say that the distribution is approximately normal. So here's what that says. It says that as n increases, so as your sample size increases, that the sampling distribution of P is going to become approximately normal. Here's what you have to check. So if you're wondering how large would you need it, here's what you have to look at, is that n multiplied by P has to be greater than or equal to 10, and also n multiplied by 1 minus P must also be greater than or equal to 10. So let's look and see how we can use these in some context to answer some questions. On the next page, in this example, it says that about 75% of young adult internet users aged 18 to 29 watch online videos. Let's suppose that a sample survey contacts an SRS of 1,000 young adult internet users and calculates the proportion p hat in the sample who watch online videos. What is the mean of the sampling distribution of p hat? Well, this is going to be pretty easy to find because remember the mean of p hat is just the same as your p-value from your population, and it told us that 75% of young adult internet users watch online videos. So what I can say is that the mean for my sampling distribution p hat would be 0.75. Here it is going to be important, if you're not already in the habit of writing percents as decimals, to start to do that. So make sure that 75% as a decimal is 0.75. Next, it asks us to find the 10% or the standard deviation of the sampling distribution of p hat, and it does also say to check that the 10% condition is met. So let's start there. Let's check that the 10% condition is met. So for our 10% condition, we're going to check that 10 multiplied by n is less than or equal to capital N. Keep in mind the simple random sample was of size 1,000, and so if I were to take 10 multiplied by 1,000, is that less than or equal to n? In other words, is it reasonable to say that there are more than 10,000 young adult internet users aged 18 to 29? And I would say yes, that's a definite reasonable assumption to make, that there are more than 10,000 young adult internet users. So now that we've been able to establish that, let's go ahead and calculate what our standard deviation is here. So remember that to calculate our standard deviation of p hat, we're going to take the square root of p multiplied by 1 minus p over n. So for this particular problem, that would be the square root of 0.75 multiplied by 0.25 divided by n, which was 1,000. And then let's go ahead and type that into our calculator now. So we'll go ahead and take our square root of 0.75 times 0.25 divided by 1,000 is going to tell us that our standard deviation is approximately 0.01369 if I go out to that fifth decimal place. Next, let's go ahead and see if our sampling distribution of p hat would be approximately normal. In other words, let's do some practice with checking our large counts condition. So for large counts, we're going to check two things. The first is we need to check if n times p is greater than or equal to 10. Remember, n here is 1,000, p is 0.75, and when I multiply 1,000 by 0.75, that comes out to be 750. Is 750 greater than or equal to 10? And absolutely. Next, let's check that n times 1 minus p is also greater than or equal to 10. So now we're taking 1,000 multiplied by 0.25 and seeing if that's greater than or equal to 10, which comes out to be 250. Is 250 greater than or equal to 10? And absolutely it is. So what we can say is that by our large counts condition, the distribution of p hat is approximately normal. So what all of that leads us up to is now let's say we wanted to calculate the probability, or let's say if our sample size increased to 9,000, okay? So let's say our sample size went up to 9,000 instead of 1,000. how is that going to change our sampling distribution of p hat? Well, let's talk about the three different things we were just discussing. Let's say we look at the shape, let's look at our center, and let's look at our spread. Well, for shape, if you think about it, if our sample size increases to 9,000, then pretty clearly when I take n times p and n times 1 minus p, those are both going to be greater than or equal to 10. In other words, our shape of our distribution should be the exact same. It should be approximately normal. Same is true of our center. When I increase my sample size from 1,000 to 9,000, remember, center does not depend on that. My mean for my sampling distribution of p hat is still equal to 0.75, so that's still the same as it was before. So what is going to be different is the spread. And so obviously when we're thinking about spread, if we increase our sample size, then our spread should be less than before. Let's go ahead and just calculate that to be sure. And so first, let's go ahead and make sure that 9,000, if I check 10% condition there, is it reasonable to assume that there are 90,000 young adult internet users? And I would still say yes, there are still plenty of 18 to 29-year-olds using the internet, so we shouldn't have any issues there. But let's go ahead and calculate our standard deviation for p hat now. So we'd have the same numerator, 0.75 times 0.25, but now over 9,000. And so then if I go ahead and calculate that, I'm just going to use my previous entry here on the calculator, change my 1,000 to a 9,000, and that's going to tell me that my standard deviation is 0.00456. So it's not 9 times less because it's under a square root. And so keep in mind, 9,000 is 9 times the size of our original population. But if I take the square root of 9 is 3, then this standard deviation is 3 times smaller. So our standard deviation here is 3 times smaller than it was before. In fact, if you were to take your previous standard deviation, divide that by 3, you'll see that that comes out to be the exact decimal that we just found. So be careful when you're comparing the two, because it's not going to necessarily be 9 times smaller, but take the square root of 9, it is going to be 3 times smaller. So let's go ahead and talk about how we can possibly use this to answer some other questions. So let's look at this next example. It says the superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Let's suppose that 80% of all middle school students in her district are planning to attend a four-year college or university. What is the probability that an SRS of size 125 will give a sample proportion of at most 75%? So when I'm looking to find a probability, what I'm hoping to be able to do is use normal CDF. And what I'm really hoping for is to be able to find this probability. What is the probability that our sampling distribution p hat comes out with a value less than or equal to, or at most 75%, so at most 0.75. Now, here's how I would like to be able to find that. I'd like to be able to use normal CDF, where I pick something very small for my lower, 0.75 for my upper, and then here's going to be the problem though. I need to know a mean and I need to know a standard deviation in order to find them. I also need to know that it's approximately normal. So here's what we're going to do. Let's go through and check all of those conditions, similar to what we did on our previous problem. First of all, the mean for this distribution p hat, remember, should just be the same as it is for our population. In other words, where it says that suppose 80% of all middle schoolers in her district are planning to attend a four-year college or university, then that means that our mean for our sampling distribution of p is 0.8. And remember, we can say that without any other conditions being met. So in other words, I now know my mean is 0.8. Next, let's go ahead and do our standard deviation now. So remember though, for standard deviation, we first need to check our condition. So our 10% condition, let's see if that's met. Remember, our sample is of size 125. So if I take 10 multiplied by 125, is that less than or equal to n? In other words, is it reasonable to assume that there are more than 1,250 middle school students in this large school district? And I would say yes. If it was a medium school district or even a small school district like Mays, maybe that's not the case. And in a large school district, I would say that's a very reasonable assumption to make, that there are more than 1,250 middle school students. So let's go ahead and calculate now our standard deviation. So our standard deviation for p hat would be equal to the square root of, we'll take 0.8 multiplied by 1 minus that, so 0.2, divided by our sample size of 125. We'll go ahead and type that into our calculator. So 0.8 multiplied by 0.2 divided by 125 is going to tell us that our standard deviation is approximately 0.0358 if I go to that fourth decimal place, which is now my standard deviation that I can put up here. I'm just going to say 0.04, but in my calculator, I'll make sure to use the full decimal. So the last thing I need to establish before I can go straight to putting this in my calculator is I do need to establish that this is approximately normal. So I'm going to go ahead and check my large counts condition. For large counts condition, I'm going to take n times p, so 125 times 0.8. Check to make sure that that is greater than or equal to 10, which 125 times 0.8 is 100. Is 100 greater than or equal to 10? And sure is. Next, we'll take 125, multiply that by 0.2. Check to make sure that that is also greater than or equal to 10, which 125 times 0.2 is 25, and 25 is also greater than or equal to 10. So by our large counts condition, we can say that the sampling distribution is approximately normal. So because I know that it's normal, and because I now know what the mean is and I know what the standard deviation is, I can go ahead and use my calculator as well as normal CDF to go ahead and find that. So I'm going to go ahead and do that now. So I'm going to go ahead and go in here to normal CDF. For my lower, something very small. For my upper, 0.75. For my mean, remember we found that that was 0.8. And for standard deviation, I'll go ahead and type in the exact expression we used. That was the square root of 0.8 times 0.2 divided by 125. That way it gives me an exact value rather than an approximate one. And when I go ahead and paste that in here, it's going to tell me that my probability of that is approximately 0.08. And there would be my probability. So it looks like the probability, again, that my sampling distribution p hat comes up with a value less than or equal to 0.75 is going to be 0.0811. And keep in mind, we had to go through and check all of that just to be able to calculate that probability. We can't assume that it's normal. We can't assume what the mean is. We can't assume what the standard deviation is. Those are all things we need to go through and calculate for. All right, guys, hopefully that gives you a pretty good idea of what to expect with sampling distributions for a sample proportion. Until next time, have a good day.